Bounds and error intervals are terms you may come across in questions, which in fact are going to relate to a very similar thing, basically the same style of question. Now, if we're talking about bounds, we're talking about rounding, wherein a number has been approximated to a given significant figure that it's closest to. The way we determine how something is going to round is if it ends in either a 5 or a 9, it's going to round up to the next digit. So 5 will round up to 10, 16 will round up to 20, and so forth. But if it ends in a 0, or from a 0 to a 4, it's going to round down. So like 31 would round down to 30, 114 would round down to 110. Now, with this in mind, what a question may give you is a number that has been rounded. It has been done to one significant figure, to two significant figures, to the nearest 10, something like that. And it will want you to work out either just what the lowest possible values could actually be, the highest possible value, or, using both of these, the error interval. So just to get some examples to start off with, say we were starting with the number 3, and we've been told this has been rounded to the nearest whole number, so that's to the nearest 1. Now, in order to work out what your upper and lower bound is going to be, you basically add or minus half of the thing that you're closest to. So if we're to the nearest 1, well, half of 1 is a half, so we'll go a half in either direction, making the lower bound 2.5, and the upper bound 3.5. Here, as we can see with the 2.5, because that ends in a 5, it would round up to 3. Anything lower than that would round down to 2. So the 2.5 has to be the lowest possible value that could round up to 3 to the nearest whole number. 3.5 then, on the upper bound, yes, technically in itself should round up to 4. However, what we'll say is that if it was 3.499 infinite nines, 9 recurring, that would still round down. Now as for 3.5, yes, technically this should round up to 4 because it ends in a 5. However, what we'll say is that 3.499 infinite nines, 3.49 recurring, would still round down, yet it's so infinitesimally close to 3.5, we might as well just use that. If this was part of an equation that you were doing, if you were to put into your calculator the 3.49 recurring, the answer it gives you would be basically the exact same as if you'd used 3.5. To get around this though, what we'll say when we're doing the actual error interval, that is to say an expression for the range of values that this thing can actually be between, is we'll give the lower bound, in our case here 2.5, is less than or equal to, let's just say our unknown is labelled x, but then only less than the 3.5. So it can be 2.5, but it can't be 3.5. It's only going to be less than that. Okay, for another example then, let's say we have 20. Now here, rather than being rounded to the nearest whole number, this has been rounded to the nearest 10. This means that when we're doing like half of that thing it's been rounded to on either side, half of 10 is 5. So we'll be going 5 in each direction, making the lower bound this time 15, not 19.5, and 25, not 21.5. You always want to be careful in these questions. Pay attention. What has it been rounded to nearest of what? Is it to the nearest whole number, nearest one significant figure, nearest 10, so forth. And again, this would then be 15 is less than or equal to x is less than 25. For 7.9, let's say this has been rounded in the nearest one decimal place, or half of one decimal place, so half of 0.1 is going to be 0.05, which means here, for the lower bound, 0.05 less than 7.9 is going to be 7.85, and the upper bound is going to be 7.95. Again, you can spot with all of these, we're basically just adding a 5 onto the end of the last non-zero digit. Not always, to be clear, but just... So what you may be noticing as we're going through this is basically we're just adding a 5 after the digit that's been rounded to. And if it's the upper bound, that digit then stays the same. So here was 7.9, it stayed as 9.5. 20 was 25. And then for the lower bound, that last relevant digit goes down by 1. So 7.9 became 7.8. The 20 became a 10 and a 5 for the 15. In our last example then, just with the 4.61, again, we'll say this has been rounded to 2 decimal places, or 3 significant figures. You could also argue this has been rounded to. Well, so that means it's got 0.01 is the degree of accuracy it's been done to. Half of this will be 0.005. So 0.005 less than this is going to be 4.605, and the upper will be 4.615. Alright, well, if we're happy with this, then let's just give you an example of your own to see how you get along. The number 2,400 has been rounded to the nearest 2 significant figures. What is the error interval? Okay, if you just want to pause the video and have a go for yourself. And then okay, and let's just say that this is a value of x, just so you have a value to put in the middle of your error interval. Alright, if you now just want to pause your video to have a go for yourself, and then press play again when you're ready to compare. Alright, so if this has been rounded to the nearest 2 significant figures, that means it's been done to the nearest 100, is specifically in this example. Half of 100 is going to be 50, so we'll be going 50 in either direction. This means our lower bound is going to be 2,350, and the upper bound is going to be 2,450. To make an error interval, though, we'll now say that the lower bound is less than or equal to this x, and that's less than the upper bound. Alright, if we're happy with that, let's have a go at an actual exam question. So here we're given that m is equal to the square root of s divided by t, where s is 3.47, correct to 2 decimal places, and t is 8.132, correct to 3 decimal places. By considering bounds, work out the value of m to a suitable degree of accuracy, and you must show we are working and give a reason. So it's already told you you're going to be using bounds. And what it means by a suitable degree of accuracy is basically saying, if we were to find the biggest possible value of m and the smallest possible value of m, they should be able to round at some point to the same number. So you're saying, regardless if you took the most either extreme, m is still going to have this sort of value. Here though, because now we have numbers that are being put into an equation, we'll have to consider which bounds we want to take of each letter in order to get the maximum or the minimum m. So starting with s, if that is 3.47, and that's in 2 decimal places, the lowest value it can actually be is 3.465, because they've added a 5 on the end and the 7 has gone down by 1. And the upper bound is going to be 3.475. As for the t, if that's originally 8.132, the lower bound is going to be 8.1315, and the upper bound is going to be 8.1325. Now, in order to get the biggest m, because this is a fraction, we're going to want the biggest possible numerator and the smallest possible denominator. This is so that we'll have the biggest possible number divided by the smallest possible number. A big thing split into the fewest parts will give the biggest overall value. As for the minimum value of m, it'll be the other way around. We want the smallest possible numerator divided by the biggest denominator. So the smallest starting number split into the most parts. Well, for the first example then, we're going to therefore have the square root of 3.475 over the 8.1315, and for the lowest value of m, we're going to have the square root of 3.465 over the 8.1325. At this point, you'll just put them into your calculator. And if you do that, for the first, you'll get approximately 0.22924, just to do it to, say, arbitrarily 5 decimal places. We're going to round more in a second. And for the second one, we would get 0.22889. Now, as you can see, these are clearly different values. The top one is bigger than the bottom one, which makes sense because we've got the maximum and the minimum values of m. But if we were to go to just 3 decimal places now, that would round the top one to 0.229, and the bottom one would also round to 0.229, with these now being the same as each other. So, to a suitable degree of accuracy, it's also suitable because it's the same number of decimal places as our t, which had the most decimal places of the originals, our value of m would be 0.229.